Swayam Prabha, free DTH channel for education.
Hi students, welcome back to the online video lectures of the medical imaging course. In the last video lecture, we had looked at the Bloch equation, and this Bloch equation we are having it in the form of an first order differential equation. Now in this video lecture, we will be looking at the solution of this Bloch equation, and particularly we'll be looking at the solution when the object to be imaged or scanned is a homogeneous object. By homogeneous object, we mean that it has same nature of atoms everywhere. In other words, this object, when kept under this magnetic field, the T1 or T2 values, these constants, would be same for all the spins within that sample. And the second one, we would consider the assumption here is it is under uniform field. So always here we consider that the magnetic field or the overall magnetic field you are applying is in the direction of z, but spatially also if it is same everywhere, then you call it the Bz component the same everywhere. Okay, so then you call it as a uniform field. That's the case we will be taking a look in this current lecture. Okay, so what I would also do here is first let me write intuitive expressions for these the resulting magnetic fields, and then we will do a thorough derivation of those equations. So we will be looking at the magnetization vector in two directions essentially. One is in the transverse plane, what's the magnetization field we will be looking at, and along the longitudinal axis, what's the value. So this you could call it as, for example, the one which is along the longitudinal axis, you could call it as mz of t. The other one will be along the xy plane, so mxy of t. So this you commonly will be referring simply as m of t also here, because this is where you keep the B1 RF coil through which you would be receiving the signal and doing it. So this we would be calling it as m of t. So let me first write some intuitive expressions for mz of t and m of t, and after that we will do a thorough derivation of that. So let's start with mxy of t, which I would be from now on would be simply referring to it as m of t. Okay, consider the case where this you already used, we are talking about B naught field only here. So assume that you have given the B1 excitation and made it to tip onto your xy plane, so that has already tipped onto the xy plane, so somewhere it is there on the xy plane. So assume that this has a value of m naught. Okay, now we have seen in our previous lecture also what would happen to this m naught if there is no T1 relaxation. Okay, there is no T1 relaxation or no T2 relaxation. In those cases, this keeps rotating here with a frequency of e per omega naught, right? So then you could write it as m of t equal to, if its initial value in the xy plane is m naught, this would be rotating with a speed of e power j omega naught t. This is your x-axis and this is your y-axis. Now T1 relaxation is associated with the longitudinal one, and T2 relaxation is associated with the transverse relaxation, or its value in the transverse plane. So if it is there, what would further happen here is it would be decaying this value. So how would that behave if you have that value? Assume that you initially have a value of m naught, Now it would rotate still with the same value, but its magnitude would be falling down exponentially with the time constant of t2. So how can you write that? E power minus t by t2. That's all. This would be, let me write it as simply m of t. The value of magnetization which is measured in the transverse plane would be equal to m naught into, where m naught is the initial value, rotating in the xy plane with a frequency of omega naught. So this would be m naught into e power j omega naught, and its magnitude is decaying by a exponentially by a factor of t2, so that would be equal to e power minus t by t2. Okay, then let's also write the expression for the magnetic field along the z direction. What would happen to that? Say if you consider a case where you tipped it completely to the xy plane, right? So then once, because of this t2 t1 relaxation, this would bring it back to the z axis. So because of this would be brought back to the z axis here. The magnitude of it be the m naught, if you consider the value to be m naught there. So this m naught would it would over the time, so e power minus t by t1. Okay, so pay attention here. So initially it is 0 at t equal to 0, this is 0, and for sufficiently enough time, which is dependent on the time constant t1, which is longitudinal, associated with the longitudinal relaxation, this would become m naught times 1 minus exponential of minus t by t1. And suppose if your initial value is not 0, if your initial value is, let's say, mz of 0, then of course this you could write it as this would be decaying, and this finally it would reach a value of m naught. This is pretty intuitive on what it would happen, but now we will also do a rigorous derivation of it, so that when we generalize it later to from uniform sample to a non-uniform sample, right? And similarly from a uniform field, magnetic field, to spatially varying magnetic field, it would be very convenient for us to generalize based on the way we are going to derive the expressions. So let me now take you through the derivations of these equations, which we have right now seen just right away intuitively. Okay, so as I was mentioning, now let's go through the solution for Bloch equation when you have a homogeneous object and a uniform magnetic field. Let's start with the differential equation that we have come across in the previous class, where the derivative of the magnetic field with respect to t is equal to the cross product of m bar with b bar, the term responsible for precession around the z-axis, and the second term which is associated with the t2 relaxation in the transverse plane, and the third term which is responsible for t1 relaxation in the longitudinal axis, right? So now what our goal is, as I mentioned, we are considering a homogeneous object and a uniform field. To begin our derivation, we will be making further three assumptions, which we would, as we move on, we would slowly lift each of those assumptions and take a go towards a generic case. So what we are going to assume here is, initially assume that the B1 that you have applied, the RF frequency that you have applied, made your M bar magnetization field to come into the XY plane completely. So that's the first assumption. And even further, I am assuming for the convenience of the derivation that it is along the x-axis. Okay, so that's the second one. And also in the derivation, for the time being, we will ignore the effects of T1 and T2, and then we will gradually incorporate them into our formulation, right? So the moment you have ignored this T1 and T2 relaxations, all you have is this equation dm bar by dt equal to m bar cross product of it with gamma times p bar. This is the equation for us. Now your m bar, okay, this is varying with x, y, z and time, and of course dependent on x, y, z and time as well. It has three components, okay. It has at mx, my and mz, right? Now what we would like to do right now is, for this cross product, what would be the resultant of this cross product? That's what we are going to work out, compute now. Notice here the b bar, all that you are going to apply here is just along the z axis. In other words, if you consider this b bar of t, which is varying over time, to have three components bx, by, bz. Notice that this at every xyz locations, this b bar vector could have all these three components, so that distinction has to be clear. And then this bz of t, only you don't have bx, by. There is only one field that you are applying along the z axis, right? So that is what we are considering it as b naught, okay. A constant uniform magnetic field is applied. Now you compute m bar cross product of it with gamma times b bar. So that, if you, how do you compute it? You are all pretty familiar with the cross product. So this is how x cap, y cap, g cap are the unit vectors in the xyz directions, mx, my, mg, and this b bar has only b naught, gamma times b naught, with which you have to, you multiply it with the gamma. So 0 0 gamma times b naught, okay. So that you would realize now x bar into you just ignore this first row and first row and first column, and then take the determinant of the rest. So my times gamma into b naught minus 0, right? And then alternatively positive and negative, so minus y bar times, now you ignore first row and second column, and then take determinant of the rest. That would give you mx times gamma times b naught. And then we are rewriting it in a matrix form, where you could, for example, see the first term is my multiplied with gamma times b naught. So basically mx is something which is there in the direction of x, right? So that you could now rewrite as shown here. So this cross product is equivalent to gamma times b naught into m by, okay. That's what you have here. That's the first one is your x component. The second multiplication you are getting for the y component. So how can you write that? So this, you want to multiply mx with gamma times b naught, that would give you the y component. So here minus gamma times b naught 0 0 multiplied with mx, my and mz. And finally z component is, anyway it's not there, so 0 0 0 times mz. Now with that, this is your resultant. So these are the, now you come back here, dm bar by dt is nothing but, it's basically dmx by dt into x bar, right? You are taking that component of the left hand side in the x direction is dmx by dt. Similarly dmy by dt and dmz by dt, this is equivalent to, you are going to replace this cross product here with the multiplication of vectors that you got here, right? Now you could see them as three equations. Now you take each multiplication. For example, you take the last row, yeah, sorry, made a small correction here, dmz by dt equal to 0. So your mz of t is going to be 0, particularly when, since you are assuming that this is already in the xy plane and there is no t1 relaxation happening, so your mz of t equal to 0. Now you could see here dmx by dt is dependent on y component and dmy by dt is dependent on mx component, right? So you need to deal with them together. So this is where you again a classical example where complex analysis would come to your rescue to simplify things. So you would rather, instead of dealing separately with x and y components, here you deal with them using the complex analysis. For example, your dmx, now you define a new variable mxy of t, which is on the x-axis. You have the x component and the imaginary part is your my component. So anytime if you want what's the component associated with mx of t, take the real part of this complex number and imaginary part will give you my of t. So the derivative of mxy of t by dt would be equal to derivative of mx of t by dt plus j times derivative of this my of t by dt. Since you have considered this is your equation, right? So you take derivative of this with respect to t is equal to derivative of this term with respect to t plus j times derivative of this with respect to t. So that's exactly what you are going to do here. So that would give you gamma times b naught into my of t minus j times gamma times b naught mx of t. Again, you could notice here minus j times gamma b naught. If you take out, please pause the video here and work it out in your notebooks, then this will be quite obvious to you. So minus j times gamma into b naught, if you take, you will get here mx of t plus j times my of t. So this is nothing but your mxy of t. So what you eventually arrived at is derivative of mxy of t with respect to t is equal to minus j times gamma times b naught into mxy of t. This is a very typical differential equation for which the solution would be mxy of t equal to mxy value at t equal to 0 times e to the power of minus j times gamma into b naught into t. So you could see here when you are taking a derivative of it, this multiplication factor, when you are taking derivative of this mxy of t, that's where you would be getting this multiplication factor, and this initial value whatever you have is mxy of 0 here, right? So that's exactly what we have seen in our intuitive expressions when we have written these expressions intuitively. So this m naught, the initial vector, would keep rotating here with a frequency of omega naught, which is equal to gamma times b naught, right? That's what you have got here when you are ignoring the T1 and T2 relaxations. Of course, T1 relaxation will be having no impact here because that's about longitudinal one. What we need to now further include is the transverse relaxation. So as I mentioned earlier, although we are computing the mxy component, once you have this is very easy to formulate and represent because then it is just one vector rotating with the same magnitude m naught in the xy plane. So given that, you could any given point of time, if you want the x and y components, it's simply writing it as e power minus j omega t as cos omega t omega naught t minus j sine times omega naught t, right? So that would give you the mx and my components, which is m naught times cos omega naught t, and y component will be minus m naught times sine omega naught t. Now let's keep everything together. So that would be mx of t, my of t, mz of t. This anyway is 0. We calculated earlier, particularly when we are ignoring the t1 and t2 relaxations. So this is the expression that we have got there. Now we start generalizing it further. Now what we are going to do is, suppose if this is not at all starting here, if it is starting somewhere else, right? Then what is going to happen for it? You notice here this would still getting rotated with a frequency of omega naught, which is gamma times your b vector, but just that your initial point is different, so you just need to rotate it. So again notice here this is rotation around the z axis, right? That is one thing. Now that's one thing where our third assumption was that we are having it along the x axis. So if it is not along the x axis, all that it is going to make a difference is it's that vector, initial vector, would keep rotating with a value of omega naught. And then the another one is, suppose you have a component in the z value also. So when there is no t1 and t2 working on it, so at that z itself, suppose you, instead of this vector, this is your z axis, this vector being like this, suppose you have some z value also, so it keeps rotating at that particular value. So again, this rotation is with respect to the z-axis. So simple way of looking at it is, you have already seen the rotation of axis, right? The initial axis, say for example, refer back to how we derived equations in case of radon transform, right? If you are rotating around z-axis, that's equivalent to multiplying with cos omega naught t sin omega naught t minus sin omega naught t cos omega naught t. See, that's simply equivalent to rotating your xy axis. Okay, that's exactly the transformation of coordinate axis we have done in case of radon transform, where we are going to project at different angles, right, parallel rays, and that time we were rotating the axis. So all you need to do right now is your initial values of mx of 0, my of 0 and mz of 0 need to be multiplied with cos omega naught t sin omega naught t minus sin omega naught t cos omega naught t, right? And in this transformation, whichever z value you have initially, let's say at that value itself it is rotating, so that would be equivalent to just there is 1 here. So this would eventually equivalent to rotating given values around the z-axis. That's what it would give you. So that I am writing it now, this vector as rotation around z-axis with omega. At any point the rotation is given by omega naught times t into the initial vector of this m bar is denoted with m superscript 0. Hope that is clear. Then what are the assumptions that we have to lift now? XY plane, first assumption has been removed now. Second assumption of being on the x-axis is removed. All that is we are left with is introducing T1 and T2 relaxations. That's what now we are going to do here. So we will come back to our initial expression that we have with T2 and T1. So where these are the two additional terms that are associated with T2 relaxation and T1 relaxation. Now we want to write expressions for dmx by dt, dmy by dt, dmz by dt. So when only this term is there, we have done this cross product and we have written this expression. Now you have these two expressions as well along with it, right? Along with this matrix, we need to include these matrix. There is just a linear combination you could see here. So additionally, for mx you have minus 1 by t2, so that has been kept here, minus 1 by t2 for mx. Okay, and I'm looking at the terms associated with the t2 relaxation, and for my there is again a term minus 1 by t2 that should come for the expression for dmy by dt, is it not? Because this is the term associated with my, multiplication with my there. So this minus 1 by t2 has come here, minus 1 by t2 times my, right? And here as far as mz is concerned, there is a term of minus 1 by t1, so that has come here, and also there is a constant here, nothing to do with mx, my, mz. Note here, this is something getting multiplied with mx, my, mz, and a term which is giving you kind of constants. So the constant that you have here is m naught by t1. This minus and minus gets cancelled out, so m naught by t1, right? This is the now expression once you have included both t1 and t2 relaxations. So with that, how do you find the solution now? See, if you ignore these terms which are there diagonally, as well as if you ignore these terms, you already have a solution. So this matrix you could in fact write as multiplication of two matrices, right? And then you could solve them out, which would eventually give you e power, if you write it for mx, my, mz now expressions, this would give you only that matrix will have these diagonal elements which values e power minus t by t2, e power minus t by t2 and e power minus t by t1. And while you are taking derivatives, this would be eventually equivalent to m naught into 1 minus e to the power of minus t over t1. So this is the expression that you would be getting here. So you could write now mz of t to begin with, that's equivalent to mz of 0 into e power minus t by t1, because the initial conditions now you have anyway written as m superscript 0. So that initial condition is getting multiplied m. So m of 0 you could write it as all the x m. So somewhere I might have written here, this is equal to mx of 0, my of 0 and mz of 0, the initial values of the components mx, my and mz. So this mz of 0 is getting multiplied with e power minus t by t1 there. Okay, this is anyway rotation around the z axis, so it's not going to modify the z value, so nothing to worry about that. And then plus m naught into e power minus t by t1. Notice here, for the time being, consider case where your mz of 0 is 0, where it is just tip to the xy plane. So then this is the expression that we have written here. If you notice here, this is the same expression that I have written here, mz of m naught into 1 minus e to the power of minus t by t1, plus if you have an initial condition, this is what you are going to get there. Then if you look at the solution in the xy plane, again for the same reasons that we discussed earlier, that this mx of t is dependent on the other component there. So again you write it as a complex number, combination of mx and my. So m equal to, I'm just repeating the same steps, dm by dt equal to this. Now I'm again writing the expression here for dmx by dt and dmy by dt here and solving that out. So dm by dt is equal to derivative of mx component with dt plus j times derivative of my component with t. So you write this out here, the same thing which we did earlier with all those assumptions in the very similar line we are doing, and then that would give you this expression, dm by dt equal to minus of 1 by t2 plus j times omega naught into m. Again a very commonly occurring differential equation here. What would be the solution for it? M of 0 into e power minus, you could write e power minus t times the whole stuff here, so just written as two separate terms here, that's equal to e power minus t by t2 into e power minus j times omega naught t. So you could see here, if you are there somewhere here, okay, this would be given by your m of 0. From there this would be rotating in the clockwise direction because of this negative sign here with a frequency of omega naught. Okay, a very similar graphs, please refer if it is not very clear to you, the complex number analysis that the earlier video that we have discussed about the complex numbers, on how you represent a function like this which is rotating there. We studied, suppose your complex number, okay, the value is rotating in the xy plane, is rotating at a value of omega naught radians per second, and if it is decaying, how to write the expression for it, we have discussed it there in very detail. So that's going to be m of 0 into e power minus t by t2, this is what it bringing down its magnitude here, and then omega naught term, t term is something that's making it rotate with omega naught radians per second. So this is your expression for m of xy, right? That's all. Now anytime if you want the components in the x and y, how do you do it? The same story here, you write this as cos omega naught t plus j times sin omega naught t. The real part of m would give you the x component, the imaginary part would give you the y component. Okay, just to again bring back to your notice how the t1 and t2 relaxations will have an impact. So you could see here this in case of transverse plane, when you have this constant value of b naught applied in the z direction, that would bring it down, so that's with a time constant of t2, where on the other hand in the longitudinal plane, from if you consider it from 0, it would again bring it back to the maximum value of m naught. These are the transverse relaxations and longitudinal relaxations. As you would be measuring your magnetic fields in the transverse plane using the same RF coil that you used for excitation, so that your magnetization vector tips into the xy plane, you'll be using the same thing for measuring the signal also. So this is of what we would be measuring with the RF coil. Hope this is clear to you. So what we are going to do in the next video lecture, is we would further lift the two assumptions that we have made, that this is a homogeneous object is there and also the field is uniform. Then what is going to happen? That would be the last part of the Bloch equation that we would be discussing about, and then we will be moving into the signal aspects of it. Okay, I hope that's clear to you. See you in the next video lecture. Thanks for watching. Bye. Take care.